After logging, the username will be displayed here successfully. Then let's talk about the overview of the main interface. It is actually divided into a top navigation bar, a central main interface. The main interface is divided into left and right parts. The left side is a parameter information panel. It will intuitively display all parameters. The right side is the main interface. At the bottom is a navigation bar. We can switch the test light on or off, and other interfaces like curve and calibration. This is the user login area. Firstly, let's look at the top. This shows the current software version number. Here, it shows the communication status. Currently, it is green, indicating that our control system is communicating normally with the bioreactor. Indicating that our control system is communicating normally with the bioreactor. That is, these control parameters can function properly with the bioreactor. About user edit. It can perform user management operations. I logged in as sys, so I do not have this permission. Here is the user ID number. This is our internal ID number. It helps with later maintenance and after-sales service. This section shows the current time and date. This key is the exit button. Clicking it will exit the software. As mentioned before about the left side, it is an integrated information panel. It allows us to quickly view all current parameters. The right side is the main interface. It is designed as a flowchart, divided into 4 main modules. First is the gas path configuration, then the active pump configuration, then different parameters. And the flowchart also shows manual or automatic modes here. The auto valve can be returned to auto status via this button. At the bottom, it's the current tank. This is the test light indicator. Clicking it turns on the test light on the tank, which makes it easier to view inside the tank. Click again to turn it off. Later on, these interfaces will be explained in detail. As well as the sterilization function. Next, let's talk about the gas path. Standard vessel is equipped with two-way gas, air and oxygen. Air flows through a rotometer, then passes through a filter into the tank. Inside the tank bottom, ring-distributed spargers generate bubbles. Oxygen also has a rotometer, but it equips with an additional automatic valve. This automatic valve can be a solenoid valve or a pneumatic valve, depending on the specific configuration. It plays a role by being associated with No.2. Automatically open this valve, allowing oxygen to enter. Oxygen merges with air here into one stream, then passes through a filter into the tank. For air, we can click here to manually enter a value. For example, since I manually adjust the rotometer, this is just for convenience in recording. For example, I manually adjust it to 10 liters per minute. After adjustment, I can enter 10 here. Then the software records that PV equals 10. Of course, this value is actually unreal. It is not automatically recorded by the system, but manually entered by us, simply to facilitate later data recording and statistics. For example, during the mid-phase of cultivation, I manually increased its value. For example, I raised the rotometer to 30. After I adjusted it, I entered 30 here again. Now, the software can record it. So I don't have to check back later to see when I made this change. As for oxygen, since it is controlled automatically by an automatic valve, there is no manual input method here. This is the current standard configuration. It is actually a simple and economically practical configuration. If online automatic control is needed, to automatically adjust gas flow and automatically record the cumulative volume, we need to upgrade to MFC. The configuration can be air alone with one line or oxygen alone with one line, or as two channels integrated together, controlled by a main MFC. Besides these two gas configurations, other gases can also be optionally configured. For example, carbon dioxide, nitrogen, even methane, and other gases are all possible. For specifics, please consult sales. Next, let's talk about the peristaltic pump. For the peristaltic pump, the standard configuration includes 4 active pumps, used for adding alkali, acid, and a foamer, and a feed pump. Depending on the configuration, it could be a fixed speed pump, a variable speed pump, or a variable speed pump model from Watson-Marlow. Now let's look at the pump's specific functions. Taking the alkali pump as an example, clicking it shows the control circuit for the alkali pump. At the top is the cumulative volume. You can reset. This is control mode. Currently manual. It cannot be changed to automatic manually if it is associated with pH. When pH automatic mode is enabled, it automatically switches to automatic. This is manual mode. Manual on or manual off. Here links to a scale. Basically, the basic configuration does not include a scale, so this function is not usable. Here is the pump factor, speed, and rate. Currently, it is configured as a variable speed pump, so the speed here can be set. Maximum can be set to 100. Here is the pump factor. We can enter it manually or perform online calibration later. Now, we'll give it a 1 first. So at this point, if it's 100 revolutions per minute, the speed is 100 revolutions per minute. When I turn it on manually, the alkali pump has now been turned on. The pump icon below turns red, indicating the pump is working. The cumulative volume also starts increasing. Now turn it off. The red dot disappears. The pump stops and the cumulative volume stops. Reset means return to 0. The acid pump has exactly the same configuration. The defoamer pump adds defoamer. It is a bit different. It has an auto mode that needs manual activation. Other functions are the same. Regarding the auto mode, once enabled, we can see the indicator turn red here, indicating it is in the auto mode. Here is a foam alarm here. When foam alarm occurs, the auto mode will activate. We can set the cycle and working time under the auto mode based on pump speed and foam amount. If the rotational speed, we set very low, like 10 revolutions per minute. Then set a 10-second cycle with 10 seconds of operation. That is, it will continuously operate in time mode. Continuously adding defoamer until the foam alarm disappears. We can also set a higher rotational speed. Then set a shorter work time. At this point, when it triggers the alarm, it will operate for 5 seconds at once. At a higher speed, it will add a bit more defoamer in shorter time. Then wait for 5-second delay for evaluation. Now, I switch it back to manual mode. Now, let me demonstrate the automatic mode of the defoamer pump. We can see that the foam alarm has been triggered. At this point, defoamer needs to be added automatically. Enter the anti-foam pump. We could see that the internal defoamer alarm has triggered. When I switch it to automatic, it begins to run. It operates on a 10-second cycle, working for 5 seconds. Then it will stop. After that, it will resume operation until the foam alarm clears. Then it will stop. Next, let's talk about the feed pump. This part is a bit complex. First, the accumulated amount is also displayed. It has this function as well, and it can be reset to 0. Then, the control mode is also divided into manual and automatic. Manual mode works the same way. It can be manually activated and then manually off. This function only requires connection to the scale. Without the balance, this function becomes ineffective. As for fixed-speed pumps, their pump speed is not adjustable, so the factor cannot be modified. But this rate can be calibrated online through a peristaltic pump, or we can manually input a value. This is the manual mode. After I set this value too high, we can see that the accumulated amount will be recalculated. Then, when it is activated, this icon will also turn red. So, I'll turn it off first. For automatic mode, its function is more focused on variable speed pumps because it features a special feeding function. We can click in to check out this feature. It supports both linear feeding and exponential feeding, calculating the feeding speed through a formula, gradually increasing. Therefore, it requires the use of a variable speed pump. For fixed speed pumps, this feature is not available. No need to look at this. About plan control is normally in norm mode and can also be switched to step mode that utilizes recipe to execute automatic feeding based on a recipe. This will be explained later in the recipe section. As for feed speed, it isn't very useful. Then in time mode, we can fix the cycle time, fix the working time, or fix both. Since it is a fixed speed pump, we can only make manual adjustments to set everything as fixed. Here, it performs calculation, converting the entered value into actual value. So if we want 60-second cycle with 10 seconds of operation, after setting it up, click Calculate to send it to the system. This is pure manual input. For variable speed pumps, this is just a demonstration, as the fixed speed pump does have this function. Fix control time. If I fix the control time at 180 seconds, then perform the calculation, it can automatically calculate the required working time. If I increase it by 10 times, after increasing the speed by 10 times, and recalculate, it should work for 60 seconds within 180 seconds. Similarly, if I fix the time to 10 seconds, then recalculate, we could see it's a 3-to-1 ratio. If I chong to 60 seconds, then this should be 180. For the fixed speed pump, everything must be fixed. We should assign it ourselves. The equipment can also connect more pumps. For example, there are also feed 2 and feed 3. They will be displayed below. This will be explained later in the settings. Next, about parameters on the right. At the top is agitator. Click to open control. Before using the agitator, first, we need to click the stir button. Confirm. At this time, the stir button turns red, indicating the stir motor has been powered on. Only then can we perform some controls of the agitator. Here, on the top, shows the PV value. That is the current speed. Here, it is the set point and control mode, which can be set to manual or automatic. In automatic mode, there is a plan mode that will be explained later. Here is a manual output. Manual output is 0. That is, the output is 0 in manual mode now. 0 RPM. It's not associated with the SP value, only dependent on output percentage. Here is an automatic interval control. When automatic mode is on, we can enable this feature. For example, if I've set run for 20 seconds and work time for 10 seconds, run for 10 seconds, stop for 10 seconds, then here is a timer. This feature is special, is not needed for regular microbial cultures, so you don't have to open it. At the bottom is a speed limit for stirring in automatic mode. Left is the lower limit setting. Minimum can be set to 0. Maximum can be set to the motor's maximum speed. Here is the upper limit setting. Now, let's demonstrate. For example, in manual mode, I set my output to 10%. We can see the animation lights up at the maximum value, which is 10% of 716 revolutions per minute executing rotation. Change back to 0. Then stirring stops. Now try automatic mode. Set it lower. Switch to automatic. Now the automatic icon lights up. PV is gradually increasing. Meanwhile, the animation also starts. The system will automatically perform the judgment to keep it stable at the SP value. If we need to stop it, first switch from automatic to manual. At this point, ensure the manual output is 0. The agitators stop. Then turn off the button. Next, let's talk about pressure. Clicking here allows you to open this control loop, as this tank is only equipped with pressure detection, meaning it only has one sensor. It can monitor the pressure inside the tank online, but does not have any control function. If pressure automatic control is needed, please contact our sales team. Now let's talk about temperature. Similarly, clicking here opens the temperature control loop. Here is PV. Here is SP, manual and automatic modes. Here are some PID control parameters. Don't modify them. It will operate automatically. The deadband can be set to 0.1. If the process requirements aren't strict, we can set it larger. 0.2, 0.3, or even 0.5. Deadband. For example, currently 0.1 means from SP minus 0.1 to SP plus 0.1. That is between 36.9 to 37.1. The system will not execute any heating or cooling control. If we set it higher, say 0.5, then similarly, from 36.5 to 37.5, the system won't control temperature. Setting a larger range helps reduce frequent valve switching. But it's also less precise than 0.1. This shows output as percentage. It cannot be changed. This is a cycle time. Default is 1. Generally, you don't need to modify it. It means it evaluates once every 10 seconds. Below is cooling and heating output. Usually set to 100% before controlling the temperature. There's a precaution. Refer to the flowchart. Chilled or cool water enters below the jacket. It fills the jacket and exits from the top. From here, V53 is normally open. H51 is configured to use electric heating. So there is a level sensor. When there's no water in the jacket, it will trigger an alarm, indicating the jacket has no water. Here is a circulation pump. After normal fermentation, water will automatically flow in. This is just a demonstration. This button is for filling water into the jacket. Clicking it opens valves and also starts the pump. Thus, cold water enter the jacket, since the level sensor is in alarm state. The peristaltic pump will not start. Using pressure here, push it in. After H51 is filled with water, the alarm will disappear. Then pump P51 will open. I turn it off. Now I'll try it. Currently, SP is higher than the PV. I change it to automatic. Then the automatic mode triggers the pump to start. Since there is no water inside, it actually won't turn on. There will be PID conversion here. I need to turn it off now. To prevent dry burning from damaging the heating element, I change the set point to below the PV. For example, I set it to 10 degrees Celsius. Now I turn it on again. We can notice that this part is still red. This indicates it is in automatic mode. The cold water valve will also open, indicating cold water will be flushed into the jacket, replacing the hot water. Next, let's talk about pH. Similarly, after clicking, we could see the pH control loop has PV, SP, control mode, and PID. The deadband defaults to 0.05. We can modify this ourselves. The control cycle also defaults to 10 seconds. It's in manual mode now. Change it to automatic. After one execution, since the PV value is higher than the SP value, so it needs to automatically pump acid. We could see both pumps are in automatic mode. As acid is being added, this pump turned on. There is no value shown here because there is no factor. If I set it to 1, it will start accumulating. I won't demonstrate alkali addition, as it works the same way. Besides that, We can also link pH with feed 1. Clicking allows configuration. We can set it as forward or reverse. Forward means feeding is initiated when pH is below a value. Reverse means it's starting feeding when pH is above a value. Here we can set control cycle for the feed pump. Its settings are identical to those of the feed pump. As the value of pH is 14, which is higher than 8, I need switch to reverse mode. Then I link it. After linking, I change it to automatic. We could see all 3 pumps are now linked to pH. Because I meet the linking condition, the feed pump started running. Now I switch it back to forward mode. We can see, since it doesn't meet the condition, the feed pump stopped running. Next, let's talk about dissolved oxygen. Similarly, click. It displays PV, SP, and the control mode, either manual or automatic. For this configuration, since it only has an oxygen solenoid valve, it can be independently cascaded to speed. An oxygen loop. Let's first look at speed. Click it. Whether to increase only without decreasing step, or to increase and decrease along with oxygen changes. We could set cycle here, which means an evaluation every 20 seconds. If still not met, the speed will increase again. Here is a note. See, it can be linked together with the do PID controller. That means it will multiply a PID factor based on 10 revolutions per minute to achieve more precise control. After I turn on, we can see it is linked. But since this button is not turned on, it cannot start turning. Now I need to turn it off quickly to avoid damaging the equipment. One point to emphasize here is that only cycle and step are controlled here. If we want to set the maximum value, under cascade control, we need to set its upper and lower limits in stir control loop to prevent it from constantly reaching its maximum value, which might affect the motor service life. I switch it back to automatic here. Besides that, the cycle and step can be set according to actual process conditions. It depends on the process. Now, let's look at oxygen supply. We can choose to turn it on or off. It controls the valve V2E. When it needs to open, it will open and let oxygen in to increase due. Currently, the PV is 0 and SP is 40. I turn it on. Since it's manual mode now, it still hasn't executed, so I switch it to automatic. After a 10-second cycle, the system determines the valve needs to open. So the valve opens. This is also auto-calculated by the PID controller. It only adjusts the duty cycle of this line. So its actual flow rate cannot be calculated. So for oxygen, it's not possible to manually enter a simulated value like you can with air. Now I switch them back to manual. After independent cascade, let's take a look at linkage cascade. Before explaining cascade linkage, let's look at output limited first. Because this configuration has no nitrogen, this isn't used. Here we can further adjust the oxygen addition duty cycle. Currently, it's at 100%. Clicking here, this will be explained in more detail. For details, please refer to the memo. Here is a demonstration, mainly setting the order of cascade control. From level 0 to level 3. If DO drops low, it will progressively move through these steps. If DO rises high, it will return step by step from back. There are 4 values, which are 1, 2, 3, and 4. 1 is corresponded to stirring speed. 2 is corresponded to the airflow linked to the air MFC. 3 is linked to oxygen flow. That is the oxygen MFC. 4 is linked to the oxygen bypass. We should notice, if this variable doesn't exist, don't select it, as this system doesn't have MSC. So 2 and 3 don't exist. It can only control 1 and 4. My current setting is that when the dissolved oxygen decreases, stirring speed will increase first. If stirring speed has reached the maximum value, but its dissolved oxygen still hasn't reached the SP value, in other words, the set point will be actived. That is oxygen bypass. Now, regarding delay judgment time. Of these 3 levels, it executes via delay time. We should notice that delay time must exceed all cycle times. For example, if I set speed with 20-second cycle, then I need to set delay time more than 20 seconds. Say 30 seconds. It's a linkage switch. If we only set one, this switch shouldn't be opened. Independent cascade would be better. On the right, it displays the current level, indicating the state of control level. We can adjust this manually according to the process. Then, you can also be linked with feed. Similarly, the method is the same as pH linkage. There will be a positive or negative decision. We set up and then enable. Note that since there's only one feed, It cannot be linked to both pH and DO simultaneously. Therefore, there is a priority between them. That is, the feed will be prioritized linking with DO. After linking, it will be associated with DO. Now, when I enable pH, once turned on, it will prioritize cascading to DO. This is an important point. Next, about the valves. We can see many of these on the main interface. They're all automatic valves. And pneumatic. Regarding this one, I mentioned earlier that it normally open, meaning it remain open. After clicking, I can force it open, although it open, in auto mode, or force it off. After forcing it off, the valve icon turns gray. The same as the normally closed valves. After forcing them off, they all turn gray. After forcing them open, the icon turns blue. This allows us to manually control these pneumatic valves. And if controlling so many of them by clicking individually becomes cumbersome, there's a button here to set all valves to auto. After clicking confirm, all valves revert to automatic mode. There's also an all stop function here, which lets us stop all automatic operations with one click. For example, if I now turn on pH DO and anti-foam, clicking all stop will stop them all. Next, let me introduce the tank's SIP function. By default, it comes with medium sterilization, meaning that after the medium is added into the tank, its jacket, the medium, and the filter are sterilized together. This button serves as an entry point. This shows sterilization countdown. Clicking it allows you to view detailed settings. Let's start from the left. This shows the current temperature of the tank, 20 degrees Celsius. It cannot be modified. It is identical to this one here. We set the stirring speed here. Here is TI that represents the temperature of the steam entering the tank. TS refers to the sterilization temperature. Holding time means the duration to maintain the temperature. Finish temp. This refers to after cooling down, the temperature should return to a certain value. TC is the final temperature we need to maintain. I can briefly demonstrate here. For SIP is achieved by pneumatic valves. This lists all related pneumatic valves, their functions, and their numbers. The entire process is divided into 4 stages. First is heating. After heating, it holds the temperature. After holding, it executes cooling. After cooling, it ends. At the end, it maintains the temperature at the cultivation level. Here it shows the valve's open status. We can see V53, which is an open valve, so it remains open all the time. Hence, it is currently open here. During heating, only these two valves open. When do other valves open? When TI is reached. That is, after the steam has entered the vessel and reached the target temperature. Other valves open. For example, the steam valves and condensate valves. For condensate drainage, these will open, allowing steam into the tank. At the same time, some other valves will open after corresponding delays. After opening, when the temperature reaches TS, which is the set 121 degrees Celsius, it holds. Currently set at 30 minutes. If we want longer, say 40 minutes, that is possible. Or even set sterilization temperature to 126 degrees Celsius as well. Upon reaching that, holding begins and countdown starts. During countdown, pressure can be set. For example, when pressure is below 0.05 MPa, the V66 valve will close. If it opens, once pressure exceeds 0.05 MPa, the valve opens, releasing some condensate, thus reducing pressure appropriately to maintain balance. These steam valves are automatically adjusted based on PID calculations, ensuring steam automatically enters the tank. When the time none, cooling begins. During cooling, different valves open intermittently or based on delay time. Cooling continues until reaching TE. For example, I can set 60 degrees Celsius. At T, I think sterilization ends at 60 degrees Celsius. After finishing, these valves will close. However, the tank temperature will be maintained at cultivation temperature. Convenient for a vaccination procedure. For example, if my process requires culture temperature is 37 degrees Celsius, I can set it to 37 here. At this point, after sterilization is complete, the incubation temperature can be maintained at 37 degrees Celsius. The following is timing mode, which can be either equivalent or real-time. Generally, real-time is selected. Then there is a control parameter for holding time. PID calculation can be done automatically. No manual setting is needed. These settings are fixed here. And then there is an SIP activation option. The chart below displays the current sterilization temperature curve. When I actually perform SIP, there will be heating, holding, and cooling curves shown here, making it easy to monitor everything in one place. For unified viewing,